Hello, my name is Eli Clemens, and I am going over my stoplight code. So I set R0 as state, R1 as timer, R2 as threshold. I put R7 as it's to compare the state so we can stop, so we can jump to stop if we want. I didn't think about setting breakpoints. But first, we will execute the code. We're going to stop at state 0. So execute, and what's happening here is we compare our state to R7 where we want it to stop at. This jumps straight to stop, and then we end. So let's reset and go to yellow light, which would be state 1. So when we execute this, we have started at 0 and 1. What happened was we compared R0 to R7. R7 is 1, which is yellow, so we don't jump to stop. So now what we're going to do is increment by 1, literal 1. Compare R1 state to the timer. If it's equal, we're going to jump to change state, and if not, we're going to go to the main loop. It's going to do this 5 times until we can jump over to change state. And what happens there is we're going to reset the timer back to 0. We're going to add 1 to R0, which is changing the state to yellow. And now we are comparing the state to 3 to see if it's past 2, because it can't be past 2. And if they're equal, we're going to reset state. If not, we're going to branch to the main loop. So, and then we're going to go. Let's reset and jump to red. And it's going to do the exact same thing, but this time it's going to jump from 0 to 1 to 2. All right, and now let's go to my presentation. Instruction set architecture by Eli Clemens. What if you're trying to communicate with someone who speaks a completely different language? You'd need a translator. In the world of computers, instruction set architecture, or ISA, acts as a translator between you and the computer. It's the link between the programs we write and the computer that executes them. When we write code in high-level languages like C#, Python, or even assembly languages, we're not directly controlling the computer's electrical signals. Instead, we're communicating through the ISA. Without the ISA, every new processor design would require completely rewriting all existing software. With it, we have a standard foundation that has enabled decades of innovation. Today, I want to explore what an instruction set architecture really is and how it shapes how modern processors work. Understanding the ISA is crucial for anybody studying computer architecture. We will look at how the ISA defines everything from basic operations to complex control flow. The ISA makes the diversity of modern computers possible. ISA describes the assembly language programmer's view of a computer. The ISA tells us what the machine does. This allows us to write human-readable code that can be interpreted by the ISA to execute our code. Having a consistent ISA allows machines that are built in very different ways to run the same programs. The ARM and the MIPS use reduced instruction set computer architecture that uses simple, consistent, meaning same size, instructions that execute quickly. Complex instruction set computer architectures like the x86 have more complex instructions, but they take many more clock cycles. RISC architectures usually have more registers, while CISC architectures have fewer, relying more on memory. The ISA also determines how the processor views and accesses memory. The ISA also defines how instructions are encoded into binary. Each instruction contains an opcode that tells the processor what operation to perform, and operand fields that specify where the data comes from. The ISA also specifies addressing modes, or the different ways to locate data. In immediate addressing, the data is right in the instruction itself. In register addressing, the instruction points to a register, and in memory addressing, the instruction contains or calculates a memory address where the data is stored. The CPU contains an arithmetic logic unit, registers, buses, and a control unit. The control unit decodes instructions and controls the flow of data between registers and the ALU using buses. The ALU operates on data to determine the action of one or two operands. Registers are storage elements inside the CPU. They act just like storage elements in memory, Computers don't need registers, but they are much more efficient because of them. For example, if a computer has 16 registers, it will only need 4 bits worth of data in the instruction to locate the register. This is because 0 and 1 binary 2 to the 4th power is 16. The most important register is the program counter, or the instruction pointer. This register contains the address of the next instruction. One of the most important aspects of an instruction set architecture is flow control. Flow control is the computer's ability to execute instructions out of order using branches and jumps, subroutines, interrupts, and operating system calls. One type of flow control is conditional logic, where the computer makes a decision between two options based on certain criteria. An example of using conditional logic in ARM assembly is BEQ. BEQ checks the 0 flag and either branches if the 0 flag is set to 1 or continues to the next instruction. These information paths link the ALU with the program counter, allowing the ALU to determine whether to branch or not. Whether the branch or not is taken or not is determined by the outcome of an operation performed by the ALU. 4 flags are used to help the ISA use logic. These 4 flags are the 0, carry, negative, and overflow flags. When the ALU performs an operation, it updates the flags. Information from the ALU is delivered to the condition code register, which is then stored to represent flags as individual bits. The CCR is connected to the control unit. When BEQ is executed, the control unit selects the correct flag from the CCR. If the flag's false, the CPU ignores the branch and continues to the next instruction. If the flag is true or